Shivam Pandey, coming from Johns Hopkins. It's a brief introduction. Shivam did his PhD at UPenn. He followed this by a postdoc at Columbia, working with Colin Hill and et al., and is currently an associate research scientist at Johns Hopkins. And so Shivam's work is sort of at the intersection of cosmology and astrophysics, where I guess Shivam utilizes multiple probes such as weak lensing, CMB secondary anisotropies, and galaxy clustering in order to learn about the interplay between cosmology and astrophysics. He's done some work on multimodal approaches with simulations. He's also a member of the Learning the Universe collaboration, and has also done a lot of work in building accelerated forward models for large-scale structures. Yeah, we're really excited to have him today to tell us about bringing your own galaxies. And yeah, let's welcome Shivam.
All right, thanks a lot, everyone. It's great to be here. So today I'll be talking about developing some accelerated forward models for galaxies. And the idea is similar to how we sometimes choose to go to BYOB restaurants, right? Like, we don't want to be limited to expensive and limited set of alcohol choices. Like, we would want to choose our own theory. So the idea here is so that we are not, so if you're doing any cosmological analysis, we are not limited to expensive and limited set of galaxies and hydrodynamical simulations. We can generate them in a much cheaper way. So the work has been done with multiple people, particularly in Learning the Universe collaboration. And yeah, also feel free to interject at any point or clarify any doubts. All right. So what is the central problem, right? Like, we would like to understand what's the nature of dark matter, what's the nature of dark energy, how do galaxies form, how do supermassive black holes regulate the feedback, etc. And the way we typically do that is making observations of how the large-scale structure evolves, right? Like, through different probes. And we take these observations of probing different eras of evolution of large-scale structure, and we compare them against our theories of dark matter and dark energy. And then we try to put constraints on those theories. So as an example of how the traditional inference pipeline goes, so you start with the parameters of your theory. So for example, it could be the cosmological parameters. Using them, you generate the initial conditions of the universe. So these are typically assumed to be Gaussian. And then you let gravity do its work through the nonlinear evolution, and then you end up with the total matter field of the universe. But then you don't have access to exactly this matter field, the 3D total matter field in the observation. So you make the matter to observable connection. So for example, these observables could be the galaxies. And then you kind of measure certain statistics of the galaxies. So it could be, for example, the 2-point correlation function, how clustered the galaxies are relative to a simple random distribution. And then you make a curve like this, like what's the correlation between the galaxies as a function of how far away they are. And this forms as the summary statistics that has compressed your observation. Now you go to your data. So you have observed these galaxies. You do the same thing, like you take the pairs of galaxies, you measure what the correlation between them is as a function of distance, and then you try to compare the two. And this typically involves putting some semblance of error bars in your measurements that is captured by the covariance. You try to come up with some sort of similarity between your measurements in your data and your theory, and then you try to run some sort of sampling where you sample the parameter bunch of times in the area of interest. And that gets you these parameters. And this is the typical objective. Now, in the traditional inference pipeline, particularly if you restrict yourself to these simple 2-point correlation functions, whole top of the thing, you can replace it with some sort of analytical modeling. So you can typically have some simple ways of estimating what the correlation as a function of distance would be. But the caveat is you can only do so for very simple statistics, like, for example, these 2-point statistics. But the observations have much more information than that. So for example, in this plot, what you're seeing are 3 different realizations of the observation. So the bottom is a Gaussian field, and the top 2 are two other fields that have non-linearity and non-Gaussianity in it. But the important thing is all three of them share the same 2-point statistics. So if you measure this 2-point statistics as a function of scale, all three of them give you the same result. But visually, you can see the stark difference, right? So this sort of says that the 2-point correlation alone does not capture all the information. So you do need to have some way of extracting the information beyond 2-point if you want to constrain your theories better. And there have been multiple options that people have developed throughout, especially in past decade, of how to go beyond 2-point statistics. So typically, this involves doing some sort of nonlinear transformation of your observations, so your observed field, and then measuring some statistics on it. So if these nonlinear transformations, people have constructed some analytical ways of doing it using these marked correlation function or wavelet transforms. Or you can go all in and even use some machine learning based approaches of doing the nonlinear transformation. But the important thing is, as soon as you go beyond traditional 2-point statistics, you cannot use the traditional pipeline as is. So you cannot write down an analytical model now because things are highly nonlinear. It becomes very tricky to estimate the covariance. Again, it's very nonlinear, and you typically need too many simulations if you're going that route to get the error bars. And again, because these have become now special statistics, writing down some form of close form of likelihood also becomes very, very tricky. So to circumvent that, people have developed inspired by the machine learning literature, people are now moving towards more simulation-based way of constraining the parameters. So this is typically called simulation-based inference. And the way it works is more or less similar to what I mentioned before. So you again have your input to your theory, so cosmology or astrophysical parameters, you do the initial conditions, nonlinear evolution, matter to observable connection, and then you do your favorite nonlinear transformation, however way you want to compress these observations to some sort of summary statistics. And you again measure some sort of curve, like what the summary looks like as a function of some semblance of scale. And you do the same, or now what you do is like you do this thing for a lot of pairs of these parameters and these summary statistics. And once you have lots of pairs of these two things, you can use some neural networks to come up with this joint distribution of, or this joint probability distribution of your parameters and however you have compressed your data. But the nice thing is, like, now, if you have access to this joint distribution, what you can do is you can go to your data and you can again take the same nonlinear transformation of the data, measure the same summary as a function of scale, and take the conditioning. And this becomes your neural posterior that is of interest, right? Like, this is the thing that you would want to know. What are the constraints on your parameters conditioned on data? And this gets you the constraints on your parameters. And this has slowly become pretty standard in the field of astrophysics and cosmology, and there are lots of public tools that people have developed to do these things for your favorite set of data. But it's still not as straightforward. Like, if it were, then it would have replaced things overnight. So there are some main bottlenecks in directly implementing this sort of approach to put constraints on it. And one of the main things is that the universe is huge, and the observations that we do of the universe span a gigantic volume. And as I mentioned, like to implement the SBI pipeline, what you need are reliable simulations. So you do need some way of very faithfully representing our entire observations using some simulated approaches. So even for these surveys that ended a decade ago, so this is called STSS survey, which observed a bunch of galaxies and quasars going out to pretty high redshift or very far away in time. You can see that even if you kind of limit yourself to only talking about the galaxies, this thing, you have to go out till around 3 gigaparsec in distance. So this is like pretty large distance that becomes kind of tricky to simulate. But the most tricky part is it's not just about volume, it's also about the resolution at which you need to do these simulations. So this thing is sort of captured by the plot on the right. So I'll give a little bit more detail on the next slide, but basically what this slide is showing you is for the galaxies that are living at these sort of higher redshift, like around, say, like around at 3 gigaparsec distance, what is the typical halo mass that they occupy? So meaning that these galaxies form in these deep potential well formed by dark matters. And these dark matter form these collapsed virialized structures that have some mass associated to it. And typically you can see like these galaxies occupy halos that are of mass approximately 10 to the power 12. And the thing is, if you want to simulate something like this, going out to 3 gigaparsec at a 3 gigaparsec box, you need to simulate approximately 6,000 cube particles, which I think if you do simulations, that is in on itself is kind of expensive. But it gets, the problem gets exacerbated because you don't just need to do now one simulation. If you want to do the simulation-based inference, you need to run a lot of them, right? Like so that you can get the joint probability distribution. So we need some ways of kind of accelerating the thing. So this is the problem statement. How can we make this process cheap enough that we can get reliable simulations such that we can do the simulation-based inference and get precise constraints on our theories? Any questions till this point? Okay, if not, so let's try with things a little bit simpler. So we will try to learn the statistics of these halos. So remember, these halos are these collapsed virialized structures that get formed in these deep dark matter potential wells. And these are the structures that galaxies occupy. So if you want to learn the statistics of the galaxies, we need to learn statistics of these halos. So basically the picture is like this, like you have some sort of dark matter halo, and then this is, and like there will be a central galaxy that will be sitting at the center, but there will be other galaxies that will be sitting in these sub-halos that are distributed inside it. So we will try to just learn the statistics of this main halo, like particularly where exactly it is and what its mass is, what its velocity is, what its concentration is, etc., etc. And we will learn this using this sort of n-body simulation. So these are very, very precise simulations. So these have formed the halos reliably enough. But as I said, like it gets very tricky to go down to super low in halo masses and large and to high volumes, and also vary the parameters of your theory, like particularly the cosmological parameters. So these simulations made a choice. They limited their volumes to just 1 gigaparsec box, so compared to the 3 gigaparsec that I have mentioned before that we need to go to. And they only use 1024 cube particles, meaning that the minimum halo mass that they resolve is approximately 10 to the power 30. But the nice thing is they had run approximately 2,000 simulations that varied the parameters that we would want to constrain, like these cosmological parameters, right? So you can like, first question you would ask, why not just scale this? Like, why not just run this thing for 3 gigaparsec, increase the number of particles? I mean, I said 6,000 cube is, running 6,000 cube particles is kind of expensive, but how expensive it is? So if you just, for example, in this plot, it's showing you how much it's going to cost you in some million CPU hours as you scale the survey volume, keeping resolution the same. So even if you don't worry about going down in the halo mass resolution and increasing the number of particles. So we are here, like this is 1 gigaparsec cube volume. And the thing that we would like to go down to is approximately here. So approximately for this box size. And then like the upcoming simulations are for even larger boxes. And if you just naively scale those things with assuming, depending upon how you implement your simulation, so either n square scaling or n log n, so best case to worst case, you still end up needing like close to 200 million CPU hours to maintain the same resolution, but just increase the volume and run these many simulations. So this is already pretty tricky. Like you can imagine like this thing already will only be good enough for a decade-old observations, and also it's unclear if 2,000 simulations will be good enough. So we would like to find ways that we can accelerate this process and get the halo catalog that is of interest to us. So the way we will do it is run another sort of simulation. So these are called particle mesh simulations. So in here, what you do is like instead of solving particle-particle interactions exactly, which is the most costly part, you put all the particles in some sort of grid, and you use simple equations of motions and use tricks of Fourier transform to significantly speed up the evolution. So for example, I'll keep volume the same in here, like 1 gigaparsec cube, but I'll reduce the number of particles quite a bit, and again use this particle mesh approach to run the simulation. And I get approximately 1000x improvement in speed. So these simulations were taking 5000 CPU hours. This only takes 5 CPU hours. And if I run it on its GPU, it's gonna be like order seconds. So I will try to see if I can somehow map this simulation to the output of the simulation. And you can imagine, right? Like I cannot just take the thing on the left as is. Like I do need to learn this mapping because I have made so many approximations in running the simulation on the left. I cannot just go and find halo catalogs of interest. Like this thing will not have resolution or fidelity that is good enough to get you the thing on the right. But what it will have is getting you the right kind of environment, like setup of the large scale structure around a halo, such that you can learn this mapping. So this is exactly the problem. So how do we connect the thing on the left to the output on the right? So thing on the left is this low resolution particle mesh simulation. That is our input, and we want to get the 3D halo catalog distribution. So where exactly the halos are and what their properties are. So the way we approach this problem is kind of voxelize this 1 gigaparsec volume into these small voxels. So these are approximately 8 megaparsec in length. And the problem now gets translated to finding this set, right? Like what are the masses of all the halos that occupy any voxel? Conditioned on whatever the total matter field is doing around this particular voxel. So conditioned on this large scale structure, find how many halos there will be and what their respective masses would be. And the way we approach this thing in this particular work is split this conditional probability distribution into this autoregressive way. So we first estimate how many halos there will form, again conditioned on this environment. Then and as the next step, what the mass of the heaviest halo is. So that's what M1 stands for, conditioned on again the environment and the number of halos. Then the second heaviest, third heaviest, etc., until we get down to the lowest one. So to go into a bit more detail of how this algorithm works. So this is our input, remember, but we need to now, to learn the mapping, we need to encode this thing into some essential summary statistics that will inform the conditional probability distribution that I talked about. So we use these CNN-based approaches to extract the features. We particularly use this residual network approaches that will go around each voxel, and then we'll encode the properties of the large scale structure into some features that will inform the properties of the halo. And we append whatever the parameters of this particular simulation is, so the cosmological parameters, and this particularly becomes our input set, right? Like this is the thing that we would like to learn the mapping from this to the properties of the halo. Now to get you the number of halos in any particular location, we use classification by mixture density network. And this thing essentially in here, what I'm showing you is for example, the histogram of the number of halos in two different sort of environment. One is a very high density environment, and you can imagine like if you take some high density environments and try to just make a histogram, you will typically have lots of halos. So that's where you can see it peaks at 3 or 4 halos. Whereas if you're in a low density environment, you will just peak at 1 or 2 halos, for example. Then once we have done this, we will like to now understand what the mass of the heaviest halo is. And this one we learn with some sort of simple spline transformation. So you take as an input some base distribution. So this is like similar to normalizing flow techniques, right? You have some base distribution and you're trying to learn how exactly this thing, the probability distribution gets transformed, conditioned on the features that I have learned. And you can see again, the distribution of the masses and low density and high density look very different. You have to learn this mapping from the dashed curve to these curves, depending upon the environment you're living in. And again, for the lower halo masses, we again have this autoregressive neural spline flow that goes from some base distribution to some other distribution. And you can see in typical normalizing flow techniques, people go from a simple Gaussian distribution to other distribution. But in here, because we have some inductive biases of how these distributions look like, you can see the base distribution looks very different from simple Gaussian, and which turns out to be an important choice. And you can do a similar thing for the other properties of the halo. For example, how fast the halo is moving. So you can again use stacks of normalizing flows, neural spline flows to go from some base distribution to the velocity dispersion of the halos. But at this point, I would also like to highlight, like, even though this particular solution seems very specific to finding the halos, it's not so, right? Like, this is a very general problem. Typically, in lots of places, you are interested in this mapping between a continuous field to bunch of these point cloud kind of objects. And the idea here is you can use an architecture like this to learn these things, like condition on some surrounding continuous field, what are the properties of the point?
Sure. I was wondering, I mean, along the lines of like inductive biases and whatnot, like, I mean, is there anything like special about using an autoregressive transformation where, like, you know, you identify the heaviest halo and then the next heaviest, and like, I mean, is there anything special going on there, or like?
Yeah, because I think like the heaviest halo typically forms in the deepest potential well, which will be better identified with your input simulation. So typically that is one thing that you really want to get right. And that is one thing that you also have good chance of getting right with the input simulation. So that's why we first do the heaviest halo and then condition on the heaviest halo that kind of sets the dynamic of where the less heavier halo masses are. So this kind of split was important. Yeah. Thanks.
But this is more or less the same idea of like a halo finder over there, right?
Mhm.
For this particle mesh.
Yeah.
And like, how is this? Okay, like this condition is very important. Okay, this makes sense.
Is there a reason to use a density network on top and then quantize it instead of working on the discrete set of numbers?
Yeah, so if we use just some simple cross entropy loss, etc., that did not work all that well because the distribution is high. It's not very smooth. Like, in the sense it's kind of exponentially falling, right? Like you can see it's a log plot. So you have exponentially more number of halos, like more number of voxels with 0 or 1 halos, and very few with like 2 or 3 or 4 halos. And we found cross entropy loss cannot kind of struggle with dealing with the stale distribution, whereas if you do classification with this, like for these very heavy very exponentially dropping distribution, it was performed. Which is kind of like, yeah, changing. Yeah, you can even write the cross entropy loss in that way. Yeah. Okay. Okay, so moving forward to the results. So now that we have trained the algorithm there, now we would like to understand how well it performs. So we train it on some train simulation. Like remember we had 2000 simulations to train on. We reserved approximately 1800 for the training, 100 for the validation for test. And this thing you're seeing on the test simulation. So what you're seeing are a bunch of different statistics of the halos. So the top row is simple 2-point correlation, but accounting for the velocity information in very different ways. And the solid markers are the measurements directly on the simulation, and solid line is what you would predict from the trained network. And different colors in each panel correspond to different cosmological parameters, like the input that you would like to constrain. So the first thing to pay attention to is how much the statistics change once you change these parameters, right? And the second thing to pay attention to is like solid and dash, and the markers and the solid line kind of overlap with each other, meaning that the network has correctly learned the dependence of where exactly to place the halos and how, and like the statistics of it, and its dependence on the environment as well as on the cosmology.
Would this be completely off if you didn't run this, charm on the PM simulation?
Oh yeah. I mean, yeah. If you mean if I directly find halos on the PM simulation.
Yeah.
Oh yeah, there will be like orders of magnitude off. Yeah, because these are very low resolution PM simulations, right? Like maybe if you run a very high resolution PM simulation, you can get close to it, but then you won't have the computational advantage. And the bottom row goes beyond 2-point statistics. So remember, these are the things that I was mentioning. We need to go beyond the top row to because these are the things now become like these are the nonlinear transformation that become tricky to write down analytically. So the first two are the bispectra. So maybe you can still write these things down analytically, at least on large scales. But the bottom right is these wavelet transformation that is very tricky to write down. Okay, so once we have validated that the statistics are right, we would like to also do some sort of inference. So this is the thing that we would like to do on data. Like we would like to train our full end-to-end SBI pipeline, and in the end, make kind of go to our data and take the conditioning on the observed data and get inference on the parameters. And this is exactly what is done on the test simulation. So again, like these 100 simulation network has never seen. And it is only, the whole algorithm has been trained on the train simulation. The SBI has only been trained on the train simulation. And these are the test simulation that the network has never seen. And we take all the statistics that is mentioned here. We take the conditioning for each of these simulations. You can see these simulations are distributed and have different cosmological parameters, but the network is able to correctly infer those parameters as well. So it's the true versus predicted plot for these parameters of interest, and also the coverage plot that kind of tells you is your probability estimate correctly is it correctly calibrated or not? And you can see that thing also is agreeing with the diagram. So it is sort of correctly calibrated.
How many like samples do you have for the coverage test? Because I mean, it's like why?
It's a little bit in here,
Yeah,
right?
so,
I'm forgetting off the top of my head.
okay.
Yeah, but we can. Okay, all right. So let's move forward. But when I started the talk, I mentioned like the whole reason we are doing all of this thing is so that we can go beyond tests like what I mentioned before, right? Because these tests are still using 1 gigaparsec volume. But the nice thing is because once you have trained the network, it should be possible to now scale to larger volume. And this is exactly what's done here. So in here, we have run one simulation that is at significantly larger volume, so 3 gigaparsec. So this is an n-body. We cannot run thousands of these. That's going to be very expensive. But we take this algorithm that has been trained only on 1 gigaparsec simulations. We run the corresponding particle mesh as the conditioning. And then we try to see how well our prediction looks like compared to the actual measurement on this single n-body that we have run. And you can see that for the simple 2-point statistics as well as higher order statistics on right, things agree pretty well with each other. So meaning that this whole approach generalizes to large volumes. Okay, so let me, so this thing now gives you the scaling that, or like kind of resolves the issue with the scaling. So now this thing is approximately, as I said, around 1,000 times faster than running a simple n-body simulation. And this thing now you can scale to the volumes that you need for the current generation survey, or even for some future generation survey and get the constraints. Okay. There are some other robustness things that we have done. I would not go into detail, but basically we try to see if we go to some completely different simulation that has completely different gravity solver, completely different halo finder, different way of populating the galaxies. Can this algorithm generalize to those situations? And we find that it can. Basically saying that it has to correctly capture this conditional dependency of large scale structure and the property. And finally, like the actual analysis using this algorithm is going on within this learning the universe collaboration that I mentioned. And in here, you can see what are the expected gain in the constraining power as we go to these larger volume. So in here, what you're seeing is the expected constraint on the two cosmological parameters, omega matter and sigma A, as you go to larger and larger volume. So this 1 gigaparsec volume is where we are currently at. And this third point corresponds to 3 gigaparsec volume that we would want to go. And you can see that going from here to here gives you much lower scatter and these two parameters, meaning much better constraint. Okay. So this was nice, like if you are interested in the statistics that I mentioned before. But remember, one of the main bottleneck of this whole approach was that we had to start with this localization. We were taking a bigger simulation, we were putting a small box around it of around 8 megaparsec, and we were getting the properties of the halos within this box. So this thing does not have any way of getting you where exactly this point cloud, this halo was located within this 8 megaparsec. But we really do want to go to smaller scales because that's where a lot of signal to noise lives in our measurements. So if we can access these smaller scales, that will give us much better constraints on the parameters that I mentioned compared, like even in the last slide. So one way to do it would be you can treat, okay, positions are also the properties of the point cloud, right? Like we are just getting a conditional probability distribution. We can just treat positions also as the property and just train the network for that. But we effectively need to change the architecture. So we need to find some sort of architecture that is very efficient and also like highly scalable to efficiently get these conditional probability distribution in an autoregressive fashion. And this thing should sound familiar, right? Like for past 3 or 4 years, that's all the world has been doing. So all of these ChatGPT or LLM-based approaches, that's exactly what they do. They just in an autoregressive fashion try to find a scalable architecture that you can write down these very large paragraphs or sentences capturing all these long-range correlation between different properties. So that's exactly how we treated this problem. So our input becomes the PM simulation. So you can think of it as a language translation problem. You're asking the question in some language, which is the PM simulation, and you want this thing to be translated in some other language, which is the halo distribution. So we want to learn this mapping between here and here. So the first thing to do is kind of embed. So when we're training the thing, embed both of these things in the same space, right? So that we can let the algorithm train. So that's what we do here. So we take some fields in these input PM simulation, and we embed them into a given embedding space. And the way we do it is now we go a little bit more sophisticated in terms of encoding the properties. So instead of using simple residual network, we use these convolutional block attention module. So this thing is, I mean, not to go into detail, but kind of nice in taking multiple different conditional fields and properties and focusing on the region that will be important to inform the thing on the right. So kind of giving very high weight to the particular property and the particular location that will inform the properties of the halo. And then to capture the long range dependencies and the thing on the left, we use some stacks of vision transformer that is able to better capture these long range correlations in the input field. So the output of these two things is that the thing has been embedded into some embedding space, and we would like to do the same thing on the right. So to use the normal LLM approach, it only works with the tokens. So we need to somehow take these properties of the halos and effectively tokenize it. So that's exactly what we do. So we take each halo and we take its properties and the positions, and we scale everything to lie between 0 to 1. And we say, okay, the 0 to 1 range has been divided into some number of bins, so which becomes our vocabulary length. And we just find the bin value that particular property sits in. So effectively, each halo now becomes a word, right? Like a word of tokens. Then we have a space token, so we have the heaviest halo, the second heaviest halo, etc., etc. And this whole thing becomes a paragraph. So we want to effectively decode a paragraph made up of words conditioned on the thing on the left. So we take these tokens, we embed them into the same embedding space. And then we use the same architecture as has been used in the transformers based on the self-attention and cross-attention, and we finally get the output probability, right? So this has been again trained with the 1800 training simulations that I said, and then we would like to test how well it does on the test simulation. So the first thing that I will show is the performance at a fixed cosmology. So this is a single cosmology. And it's showing you, the left-hand plot is showing you how many halos sit in any particular box. So you can see this number goes from 0 to approximately 20. And on the right-hand side is what are the masses of these halos. And you can see that both the truth and the mock kind of sit on top of each other. So meaning that it captures the trend pretty well. And also the uncertainty in each of these properties look pretty simple. And but you can argue that the thing on the left or in the previous slide was the thing that it was trained on, like it is trained on getting the 1-point statistics, right? What is a much more non-trivial test is if it can get the correlations between these different halos, right? Because it has not been explicitly trained. It needs to correctly know where to put each halo and what its corresponding mass, etc., should be. So that's what's done on these plots. So this is measuring the 2-point correlations of just the position. And the most impressive plot is the plot on the right, where now each halo has been weighted by what its corresponding mass is. And you can see that in here also the mock and truth lie on top of each other. And this is kind of interesting, right? To get this plot right, the network needs to correctly learn all the conditional correlations really well, like where to put the halo, what its conditioning with the mass should be, and what its relationship to the neighboring halo should be. So you can see that network has correctly learned that. So this was for at fixed cosmology. To quickly go through the other thing without going into detail, these tests show the performance at varying cosmology. So again, if you just focus on any of the plot, that's showing you what the number of the halos are, and it's the distribution of the halo masses, the halo velocities, and the halo concentration when some cosmologies vary. And so the colors of different lines are varying cosmology, and the solid and dashed are the inferred and the truth catalog. And you can see that, again, varying cosmology changes everything by orders of magnitude. Like all of these plots are log scale. And you can see that the truth and network is performing pretty similarly. And this is saying that the network needs to correctly learn these orders of magnitude changes that can happen when you change the input parameter. So this was just the 1-point distribution. So the network has been trained to get right. And this is the 2-point distribution. So that also looks decent. So the full inference thing that I showed for the previous charm result, that is still ongoing. So stay tuned for that. But at least these tests seem kind of promising in that direction. Okay. So let's now go to our final thing. So what we actually started doing. So as I mentioned before, like we were starting out with something simpler problem. We were trying to take these input simple particle mesh field, and we are trying, until now we have been trying to infer the properties of the halos. And we were saying, okay, we'll come up with some way to populate the galaxies that we actually observe onto these halos. But it will be kind of nice if we can directly go to the galaxies and their observed properties, because remember, we do have some sort of simulations that we have learned where we have these galaxies and their observed properties. So we can try to train these kind of algorithms to directly do that. And that's what's been done here. So we now take the certain set of hydrodynamical simulations. So these are the ones that that actually form these collapse structure and galaxies and their corresponding properties. But the thing is, like, these have now, so these are much smaller in volume. You can see like these are only 25 megaparsecs in volume, and they vary some limited number of parameters, but they have run thousands of simulations varying these parameters. And again, this is our input to the theory, right? Like we would like to constrain these astrophysical and cosmological parameters. And the way we will do it is learn the mapping between these hydro simulations and these dark matter only simulations. So these ones don't have any galaxy. And conditioned on the properties of the things on the left, we would like to get the properties of the galaxies on the right. And the properties of the galaxies that we are interested in is something closer to what we actually observe. So we would like to get a handle on what the stellar mass of the galaxy is, like how many stars there are and what their corresponding masses are, what its velocity is. So this is another property. And the last property is something that is like much more closely related to observations, is the observed flux of this galaxy in the actual band of one of the telescopes. So this is STS's telescope that I was mentioning before. And this is like properly dust attenuated, etc., meaning that it will be, if this galaxy were living on the sky, like this is the flux that you would have observed. So we would now like to do the same thing. So conditioned on these input fields from the n-body simulation, we would like to get the distribution of the galaxies on the right-hand side. And the pipeline looks very similar to what was shown before, except now that we embed the properties are now properties of the galaxies. And we similarly tokenize that. And we would like to get the conditional dependencies of these tokens conditioned on the thing on the left. So one strain now we would like, so here are again the results. So this are again the 1-point distribution. So 1-point distribution of what the stellar mass of the galaxy is, what its photometry is in the STS's band, or what its velocity is. And in each panel, you can see multiple lines. So that again corresponds to the input cosmological parameter. And you can again see things shift by orders of magnitude. But the truth and the mock are approximately 1 sigma consistent with each other for all of these. So meaning that the network has correctly learned these different dependencies of different properties and on the cosmological parameters. To convince ourselves a bit more, you can even look at visually, like how do the distribution of the galaxies look. So in here again, the left-hand side is what's input. So this is the conditioning. The middle panel are the true distribution of the galaxies colored by what their stellar masses, and the right-hand side is the mock. So remember, like there is no, so the only thing that is input is the thing on the left. Everything on the right has been generated by the network by its own. And you can see that the middle and the right panel look pretty similar. On the bottom is another test simulation. You can see it looks completely different, but then again, the truth and the mock galaxies look more or less similar. So meaning that the spatial distribution as well as the relative distribution of the points are correctly captured. And finally, the 2-point correlations also look pretty similar when you change the cosmological parameters. You can see the shift is of orders of magnitude, but you can the mock and truth are 1 sigma consistent with each other. Doesn't matter if you weight each galaxy by its corresponding property or just take the spatial distribution. Okay, so this was more or less it, but just to finish, the main thing is like this quote by Eugene Wagner, right? Like it's what I've convinced you till now is that, okay, computer understands the problem, but does not mean that we fully do. So we would also like to understand why exactly network is learning all of these properties and what about the input is informing the output. So this is where we are starting to focus now. So this is still kind of preliminary, but to show just one of the preliminary plots, what we kind of are doing here is taking the inference of one of the one of the statistics. So this is a simple 2-point statistics as a function of scale. And what's plotted is the ratio of the the statistics from our network relative to what the truth is. So it should be consistent with 1. And what's shown here is what the result is when I change the input on the left-hand side. So you can see this particular line corresponds to using all the information that I can from the input simulation. So meaning that I give the input dark matter fields at bunch of different redshifts, how exactly the large scale structure has been evolving with time, how exactly like what the velocity of the dark matter is, what the environment around each particular box is, etc., etc. And you can see that is the one that does the best because I have given it a lot of information to train. But then what I start to do is like I sequentially take some of the things out in my conditioning. So just to show like one of the things like in here, in this particular line, I've taken out the velocity information in mind. And you can see like this thing kind of performs now poorly on large scales, but performs kind of okay on the small scales. So remember, this is in the Fourier space. So the large scales sit on the left, small scales sit on the right. And you can see that this particular, removing this thing as the conditioning starts to degrade the performance on the large scale. And the reason that's happening is because on the small scales, you can try to reconstruct the velocity field given the density information. But on the large scales, you really do need to give it this additional information of what the velocity field is for it to learn the statistics of this 2-point function. And there are like similar trends on the other like removing other conditioning as well. But we are like kind of taking this approach of changing the input and trying to see how exactly the output changes. But okay, so let me just conclude with this. So hopefully I convinced you that some sort of accelerated forward model is needed if we need to extract the cosmological information. And this generalizable, given how general the transformers are and how easily they process these multimodal inputs, it can be this kind of paradigm can be extended in cosmology as well. But definitely much more work is needed if we need to integrate these kind of techniques to the actual data pipeline. We need to understand why exactly the network is performing the way it's performing. Have we dealt with all the systematics well enough, etc. But yeah, thank you. Finished there.
Thanks so much, Shivam. We have a few minutes for questions.
So which like kind of you're on the right between like in both plots you see towards when the number of halos
Here?
is
That number of halos.
in both kind
Yeah.
of plots you see to the right there are deviations.
Like this thing, right?
Yeah.
Yeah, but this is like, you see, it's just 1 or 2 halos. So it's just like a random statistical fluctuation.
Yeah, exactly. And that's something. So I work in rare event
Mhm.
populations of, for example, binary black holes. And this is actually really the tricky thing of machine learning in this tails. And I see that this is way underestimated to like put also effort in these tails because there is like often also the interesting things.
No, that's an interesting question. Like in here, we don't care all that much because these halos will probably, or like these regimes will probably not impact the final statistics that we care about. But yeah, you can definitely construct some special statistics that really care about these massive halos, right? And then you do care about getting this number exactly right. Like even if it is off by 1 or 2, that's going to change these statistics quite a lot. So yeah, you're right. And because the number of examples here is kind of limited, it gets tricky. So we tried doing something in here. So when we train this algorithm, like this kind of architecture, we take the full simulation, but then we make these smaller sub boxes. Like we take a gigaparsec simulation and we'll chunk it into 100 megaparsec sub boxes, and we learn the mapping for these 100 megaparsec boxes. Now, instead of so what we do is like training on these full 2000 simulation is pretty tricky. So for each simulation, we only take 10% of the volume in terms of these 100 megaparsec sub boxes. So instead of taking a uniform subsampling of the full 1 gigaparsec simulation, we do the subsampling in a way such that the background density is effectively constant across. So that means that we upweight certain subvolumes where these rare events are happening, and we downweight the subvolumes where things are much more normal. And it's all good because we are always learning the conditional distribution, so we can play this game of selecting things. So I presume like if we do it at a little bit finer scale, I think that will get the rare event better. But yeah, we have not experimented much more.
Yeah, quick question that if you're getting the halo positions like distribution right for say some snapshot given some density field, so I assume that's like you could scale around the resolution as well about how many halos would be there, something like that. And additionally, would it be time evolving in the sense that if you do multiple snapshots, could you be able to build a merge tree of the halos out of it?
So I think that will require training it in that way. Like right now we are like all of these things were at fixed redshift. So we are extending things to get you things at multiple redshifts by conditioning things on the redshift that you are interested in. But the thing is that will still not get you the merger tree, because for that you really need to like train on itself.
Okay.
And that I think that requires a different architecture, or like at least even with the same architecture that requires changing the user train. But yeah, I mean, it in principle it's possible, but yeah.
Actually, I have a question. I mean, but also, are there any questions on Zoom you see, or if anybody's on Zoom, just raise your hand or something. So, but I think we're good.
Yeah.
Okay. Yeah, I guess I was wondering, you know, there was some discussion about, you know, when you use these transformers that you know, it's autoregressive, but there's also some notion of like longer range correlations. And I guess I was wondering like how I should interpret that like in this problem, because normally like, you know, there are, you know, physical processes that like kind of couple large scale like physical modes with small scale physics. But I guess I was wondering the way that you're kind of tokenizing, like, is that actually what you're capturing in these like long range correlations, or like
it will capture that, right? Like, because it's capturing the full for this space of tokens, like for these halos, it's capturing the correlated probability distribution of all the halos. So it is conditioned. So like halo here will be conditioned on what the halo here is doing, and all of this is also conditioned on the long range properties of the field, right? Like on the left, because that also we have tokenized with these vision transformers, etc. So like there is a notion of long range dependency.
I guess when you do it ordered by mass, you sort of accumulate the two halo information, and then that can, and anyway, yeah. Okay, any other questions? Oh, there's a couple. Yeah, you and then
Have you tried to measure the robustness of our models for camels
For
for
camels.
different hydrodynamics?
Oh, that, I mean, it would not work for different hydrosims, right? Because it is entirely conditioned on these astrophysical parameters. So like if these astrophysical parameters mean something different for different simulation, I don't think it's gonna work. I have not tested it, but I have no reason to believe it will work. So you will have to train it in like either train it for multiple subgrid physics and hope that interpolates the space well enough, but
But which camels?
This
and
was
things
TNG.
have you used? Sorry?
this was TNG.
PNG. Okay.
Yeah.
Thank you.
Can you go back to the plot with the input and the, yeah, this one. The probabilities you're learning, I got lost, I think, are conditional to the input.
It's conditional on, so it's the output probability of each token, right? Like for each token, it will sequentially learn the output probability. So for the first token, it will be entirely conditioned on just the properties of the field. But for the second token, it will be conditioned on the properties of the field as well as the token previously. For the third token, it will be conditioned on the last two tokens as well as properties of the field. So through this cross attention mechanism, like we have encoded the field into the same embedding space as all of these tokens. And through the cross attention, like it takes into account the dependency of each token on the field, but then through the self attention, it takes into account the dependency of each token on the previous token.
Okay, if I'm interested in doing exactly the opposite, learning the matter density given the halo distribution, how would you attack it? Because you need to change your tokenization.
Yeah, I don't think like then this is the right architecture, because yeah, I think like then I think using something like diffusion model, etc. is better for that, because then you're dealing with 3D fields as your output. So you can still like, people have these
maybe the tokenization is still useful.
I mean, then you can just take the actual raw properties of the halos, and I mean, the only reason to tokenize it so that we can use the simple cross entropy laws that people like still make a generative model and use the cross entropy laws. If you're only using for conditioning, which you will like if you're trying to get the thing on the left, then you probably don't need to tokenize at all. You can just take the actual properties of the halo, make the 3D maps of the properties, just pass that as the conditioning to the diffusion model, and that should get you the field on. So there have been some projects that people have done in that line, particularly like not just getting the dark matter field, but also getting the initial conditions that would have generated the halo.
Yeah, but I talked with that for Columbia.
Mm-hmm.
That for the initial condition.
Yeah.
I never got it to work on my problem.
Oh, okay. Yeah, maybe we can chat.
Yeah, Shivam's here the rest of today and also I think through next week, and may have some slots open on the schedule today. So I encourage you to chat with him, and yeah, let's thank you again.
Thanks a lot.